There we go. Hopefully you can see the presentation. So what I want to talk about here is the solar system, and this is your traditional picture of the sun, the planets in orbit around the sun. And again, when you look at that, the planets look big, they're not drawn to scale, the distances between them aren't right, but that's probably the picture that you have in your mind when you think about the solar system, because it's the picture that you see in books when you're growing up, and it's a good illustrative picture, but it's not realistic at all. Oh, someone's drawn on my screen. Who's that? What's going on there? Let me just clear that. I don't know what's going on there. So when we have a look at the solar system, I want to break it into kind of sections that will hopefully make everything make sense. So I'm going to talk about the different types of planets and moons, and collectively they're called the terrestrial planets. Then there are a different kind of planet further out in the solar system. There are actually two types. There are the gas giants and the ice giants. We're also going to look at asteroids, comets, and dust. And we'll look at the vast structures beyond the planets, the Kuiper Belt and the Oort cloud. And then finally, we have to think about where the solar system came from and how it originated. And we haven't really understood that until we started finding planets around other stars. And lastly, I want to show you how our location in the solar system on Earth influences our view of the planets in the night sky. And they kind of behave differently depending on whether they're inside or outside the Earth's orbit. So that's the plan for this evening. Okay, here we go. So again, this is an overview of the inner solar system. So this group of planets are the rocky planets, the inner solar system, going from Mercury, Venus, Earth, and Mars. If you look carefully, you can see that the orbits of the planets, someone is drawing on my screen. It is not me. What is going on there? Thank you. I don't know who's doing that. I bet that's Paul. Paul's the kind of person who would do this, I think. We will see. Right.
No, it isn't. I'm not sure how it's happening.
Yeah, okay. So anyway, these are the orbits of the inner planets, and you can see they're not quite circular. And it took a long time for astronomers to figure out that the circle wasn't the shape that the planets' orbits resemble. But anyway, if you zoom out a bit further, you can see the outer solar system. Now, the center circle in there is the orbit of Mars. So you can see there's actually all the planets, Mercury, Venus, and Earth are inside that middle circle. And then you've got a huge gap where we've discovered there is an asteroid belt. And then we've got Jupiter, Saturn, Uranus, and Neptune. Pluto is no longer considered a planet, but if it was on there, its orbit would be kind of intersecting with Neptune's and going a little bit further out as well. Now, the terrestrial planets are the ones I'm going to start with, and these are the rocky, small objects in the solar system. So the Earth happens to be the biggest of this type of planet, and Venus is the next biggest, the next massive planet. Mars looks quite small in comparison. In fact, it's just 10% of the Earth's mass. Then you've got a moon, Ganymede, which is the next biggest, followed by Titan, and then Mercury. So there's actually a couple of moons in the solar system which are bigger than Mercury. Callisto is almost Mercury-sized too. Then you've got Io, the moon, and then you get down into the really small moons of the outer planets. What these share are properties like they have rocky surfaces, and some of them have atmospheres. So the mode of formation is broadly similar for all of these objects. The terrestrial planets coalesced 4.5 billion to 5 billion years ago. Some of them still retain the heat of their formation. Some of the heat is because they were formed from objects which slammed together, releasing a lot of heat, but also some of the elements within these objects are radioactive, and the radioactivity releases energy which keeps the interiors warm or hot as well. Planets like Mercury and Mars, which are smaller, have cooled off more quickly, but we still think that they retain some kind of liquid interior within them as well. The surfaces of the rocky planets give astronomers a clue to the history of the solar system. So where you've got a rocky surface, the geological record has been preserved for that particular object, unless it's been wiped out by some kind of surface process. So you've got, for example, the picture on the left is one of the moons of Saturn called Rhea, and it's got a very heavily cratered surface. And you can actually date the surface by counting the number of craters in a given area. And on the other picture is another moon of Saturn called Enceladus. And again, it's as old as Rhea, but the surface is younger. There are fewer craters because there's been some kind of dramatic event which has reshaped the surface of that moon. So across all of the solid surfaces in the solar system, on all of the solid planets and moons, we can figure out a lot about the history of the solar system. Let's do a tour of the solar system. So we'll do the traditional tour where you start with Mercury, nearest planet to the sun, the smallest of the planets, very high density. So it's got a lot of mass packed into a small size, and it orbits at about 36 million miles on average from the sun. It superficially looks a bit like the moon, except that it doesn't have those very dark, flat, uncreated areas on it that the moon does. Its proximity to the sun means that it took a little bit longer to cool down, basically, but as it did cool down, the surface shrank by about 4%, so that Mercury is covered in these kind of scarps and lobes caused by shrinking. It's got a lot of craters. It has a very thin atmosphere, kind of. It actually has an atmosphere because it impacts, the solar wind impacts the surface and basically drives off particles, which Mercury can kind of hold on to for a short period of time. So it's an atmosphere which is probably thinner than like a laboratory vacuum on Earth, but it is still a detectable atmosphere, but it needs to be constantly replenished by processes on the surface of Mercury. Some interesting stuff about Mercury. It is a small planet, and it's affected by the sun's gravity perhaps more than the planets further away. It goes around the sun with a period of 88 days, so it whizzes around in less than 3 months. It actually turns on its axis once every 59 days. Now what that means is every 3 times that Mercury spins around, it goes around the sun exactly twice. And what that means is if you were standing on like a point on the surface of Mercury, you would see the sun rise once every 176 days. But more than that, you would, every time Mercury goes around the sun and the sun I'm trying to explain this. Every time Mercury goes around the sun and completes an orbit, it's the opposite hemisphere, which is facing the sun. Another really like mad thing about Mercury's orbit is that when early observers were looking at Mercury with their telescopes and trying to like look for markings on the surface and trying to figure out the rotation period, they were fooled into thinking that Mercury spins on its axis every 88 days. In other words, that it was tidally like locked towards the sun in the same way that the moon is with the Earth. And they were fooled into thinking that because of this kind of 3-to-2 ratio means that every time Mercury is well visible in the evening sky or the morning sky, it also happens to be presenting nearly the same face towards the Earth. So it's like every time Mercury was out, every few months Mercury's out, they look at it and they see roughly the same features, and they see it again and again, and eventually it goes out of sync, but it fooled astronomers for a long time into thinking that Mercury was tidally locked to the sun. Now this kind of like locking of the rotation is something which happens because of the irregular shape of Mercury, the elliptical shape of Mercury's orbit, and gravity pulling on the planet in a different way because it's slightly elongated in shape. You see it with some of the moons of Jupiter and Saturn as well, but gravity kind of like plays a part in this. The next planet out is a much bigger planet. It's more like the Earth in size and mass. It's actually about 82% of the Earth's mass. And this is a color image of Venus captured by, I think it was Pioneer 10. So you can't see the surface in that picture. It's just clouds. It's cloudier than Northumberland. Honestly, you might not believe that to be possible, but Venus is just constantly cloudy. The atmosphere is CO2. It's something like 98% CO2, and it's an extremely dense atmosphere. It has a runaway greenhouse effect because the CO2 gas is very good at capturing the radiation from the sun and then trapping it between the clouds and the surface, so it heats up like a greenhouse, and it makes Venus the hottest planet in the solar system. So temperatures of like 480 degrees to 500 degrees Celsius at the surface. It goes around the sun every 225 days. It spins on its axis once every 243 days. So you usually hear in books descriptions that Venus has a day which is longer than its year. It's also upside down. The planet spins from east to west, unlike the other planets which generally spin west to east. So even if you could see the sun, it would rise in the west and then set in the east. But it would take 111 days between two sunrises. So it's an unusual planet, and it didn't always look like that. We think that Venus started off looking a bit like the Earth. It probably had oceans and continents, but because over time the sun heats up as it gets older, Venus was a little too close to the sun to sustain those nice Earth-like conditions for very long. So the oceans boiled away, the water vapor evaporated out of the atmosphere, and you're left with this dense CO2 which the planet is able to hold on to. Because we can't see the surface of Venus, we have to use radar. So if you bounce radio signals off the surface and listen to the difference in time signals, you can actually map out the topography of Venus using radar. So this has been done from Earth and from orbiting spacecraft, and we find that Venus is a world which has variations that are similar to those experienced on the Earth. So the highest mountain on Venus is about 11 kilometers, about 6 or 7 miles high above the mean level of Venus. Earth is the next planet out. I know probably less about the Earth than I do the other planets, which is probably quite embarrassing. But it's the biggest of the terrestrial planets. It has a dense atmosphere of mostly nitrogen with oxygen. It has seas and oceans. It has geology, which includes volcanoes and earthquakes. It orbits the sun in 1 year, and it spins on its axis in just under 24 hours. And it has one big moon. Now, the moon is actually quite interesting because in comparison with the other planets that have moons, our moon is quite big. It's about 1/4 the size of the Earth. It's tidally locked towards us, so we see more or less the same face all the time. And its surface is a mixture of old and new terrain, so that the lighter parts of the moon are the highlands and the older, really heavily cratered parts of the surface. The dark parts, the bits that make the shape of the man in the moon, are the newer regions. These are the parts that formed when volcanoes or when you had giant impacts punching through the crust of the moon, and the magma underneath flowed up and filled in the gigantic craters. And then after that, there weren't many more craters impacting on the surface. So you've got these kind of like regions which are dark and flat with not many craters. The moon has an unusual history, and we think that the moon was formed as the result of a giant impact with the Earth not long after it formed. So it's various properties of kind of like how big the moon is, the unusual shape of its orbit. It is definitely not circular, as it goes around the Earth. That's why sometimes you have these things called supermoons, where the moon appears a bit bigger. Other planets don't experience that because their moons orbit in almost circular orbits. So there's a lot of facts about the moon that don't add up, that need a different explanation. And the explanation that we have at the moment is that something very big struck the very young Earth and knocked a bit off of it. And that went into orbit around the Earth and coalesced to form the moon. So there was no way you're going to hit the Earth so precisely that you get a circular orbit. It's actually stayed in an elliptical orbit, which has kind of got bigger with time. The near side and the far side of the moon look quite different as well. So the familiar near side has lots of these dark regions on it, but the far side doesn't. We put that down to the fact that because of the locked rotation and the way the moon formed, that the crust on the near side of the moon is thinner. So when the moon was struck by these big asteroids billions of years ago, it was more easily able to punch through the thin crust on the near side, and that allowed stuff to flow up onto the surface and then solidify. Whereas on the far side, not many impacts would be strong enough to get through that thicker crust. If we move out to Mars, the last of the rocky inner planets, again, it's about half the size of the Earth, but about 10% the mass. It's very like the Earth in other ways. I mean, even looking at that picture, you can see it's got kind of like white bit at the bottom. There's a polar cap there. It's got clouds at the top. That kind of ring around the top that you can see is it's a cloud formation. You can see clouds around the equator. The red color comes from the iron oxide, which is a big component of the rocks and the soil on Mars. It's a smaller planet, so it's not as geologically active as the Earth, so there's no plate tectonics. There's a huge amount of evidence now that water was common in the past, that water flowed across the surface, that Mars had seas and lakes. And even today, there's evidence that water exists in quantities large enough to kind of to play a part in the modern day history of Mars, that it occasionally is exposed by the Martian weather. The sunlight melts it and it kind of flows across the surface until it very quickly evaporates. So there's a lot of water on Mars. Most of it's locked up in the polar caps these days, along with carbon dioxide ice. But Mars is kind of a place where life might have existed in some form and where it still might persist. And that's why NASA and other countries are spending a lot of money trying to explore it, to try and answer these questions about, is Earth the only place that could sustain life? If we find life on Mars, or that life did exist on Mars, because it's basically the next planet we've really closely examined, it kind of shows that life could exist in many places, not just kind of perfect conditions like the Earth. We've got brilliant pictures of the surface now, and it is a dry desert-like planet with rocks strewn everywhere. So lots and lots of pictures. And every time I do a talk about Mars, I put this picture in. This is sunset at Gale crater. So it's a real color image of a Martian sunset. And for comparison, an Earth sunset, the sun would look just a little bit bigger than that. Okay, so it's hard to tell with cameras and lenses and so on, but it is definitely a Martian sunset. Now, these are kind of planet-like as well, but these are moons of Jupiter. So I'm going to show you the four big ones. These moons of Jupiter are visible with binoculars. So Jupiter's in the sky right now. And you can see the moons of Jupiter with binoculars, but the innermost big moon is Io, and it's a very volcanic moon. That color is derived from sulfur compounds blasted out from all of those volcanic vents on the surface. So just about every black splodge you can see on Io is an active volcano. The big one with the red circle around it is called Pellier. And again, it's an active volcano. The source of the activity on Io is tidal stretching. So Jupiter's gravity pulls the moon and releases it as it goes around its slightly not quite circular orbit around Jupiter every 2 days. Europa has these heating events as well, but not to that extent. But Europa has an ocean beneath that icy surface, which might be 60 kilometers deep. There's actually more water beneath the surface of Europa than there is on the Earth. Most of the liquid water in the solar system is here. The other two, Ganymede, is the biggest moon in the solar system, bigger than Mercury. And again, it's made of ice and rock, and it has an atmosphere as well. The Galileo spacecraft discovered it has a very tenuous atmosphere. It also has the biggest impact crater in the solar system on there, and it's hard to see it, especially because we're watching this on Zoom. But there was a story just a few days ago about how some of the kind of, they look like they're lines on here. I'm trying to kind of indicate them, but if you look carefully, they're concentric rings. And in the past, Ganymede was blasted by an asteroid, which almost surely would have destroyed it if it had been a little bit bigger, but instead left the biggest impact scar in the solar system. Callisto likewise has been battered by asteroids over the years, and you can see the result of that on its surface, which is just pockmarked with tiny and big craters. Another kind of planet-like object is Titan, the biggest moon of Saturn. It has a dense atmosphere of nitrogen and methane, and it rains on this planet as well, but the rain is methane because the temperature is close to minus 200 degrees Celsius. So water exists on Titan, but water behaves like a rock when it's that cold. So it does have a liquid cycle which gives rivers and lakes and weather, but it's all based on methane instead. So it's a really interesting place. Here's a picture, it's a false color image of Titan, and you can see a specular reflection. So this is sunlight glinting off one of the lakes on Titan. Because it has a dense atmosphere, you need to look at the planet with infrared to be able to peer through the clouds effectively. Enceladus is another moon worth looking at. This is much smaller than Titan. This is basically the size of England, this moon. And it's notable in the fact that it's the most highly reflective object in the solar system. It has one of the youngest surfaces. And the reason it's got such a young surface is because it's active. It has geysers and ice volcanoes which spray water across the surface. And the Cassini spacecraft captured these water vents near the south pole of the moon in these dramatic images here, and that water ejected from them, if it doesn't land back on the surface again, it actually gets sprayed into orbit around Saturn, where it forms a new ring around the giant planet. And the last moon I want to show you is a moon of Neptune called Triton. It's another big moon. This one has an unusual orbit around Neptune as well, and we think that it's been captured by Neptune because Neptune orbits close to an icy reservoir of small objects called the Kuiper Belt, and Triton is very similar to Pluto in terms of composition and size, but Neptune captured this and it became a moon of Neptune instead. It's very active. It has little black marks on there, which are actually cryovolcanoes erupting on the surface. We've only seen Triton once. It was when Voyager 2 flew past in 1989, but there's every reason to try and get there again sometime in the 21st century. Now, the giant planets, Jupiter, Saturn, Uranus, and Neptune, are actually categorized as gas giants and ice giants, because of the difference in their chemical makeup. So Uranus and Neptune have a higher proportion of things like ammonia and methane, which are icy at those temperatures. So Jupiter and Saturn have less of that. And it's also the methane which gives Uranus and Neptune their pale blue color. So methane absorbs reds and oranges very effectively, which just leaves the blues reflected back into space. So Jupiter and Saturn don't have that. The interiors are very exotic. So These planets probably all started off as rocky planets like the Earth or Mars, but because they're further away from the sun and things like the hydrogen and helium move a lot more slowly in the colder conditions of the outer solar system, these rocky planets were able to pick up the hydrogen and helium and grow to these enormous sizes. So Jupiter was the first planet to form, and it gobbled up all of the hydrogen and helium in the vicinity until there was none left to take. Saturn was similar, but with less hydrogen and helium to draw on. Uranus and Neptune had even less further out, but they're all very big planets. Jupiter is the biggest planet in the solar system. It's 318 times the mass of the Earth. It spins really quickly. I've been trying to get pictures of Jupiter with a CCD camera over the last kind of couple of months, and you can't take a picture of Jupiter or a series of images of more than 1 minute, and then the thing gets motion blurred because it's spinning so fast. It spins once every 9.8 hours at the equator, and because it's not a solid object, those different bands that you can see in the picture spin at different rates. So by the time you get to the poles, it takes about 10.5 hours to rotate. It's made of hydrogen and helium. It likely has a rocky core, 12 times more massive than the Earth. It has a long-lived storm in the atmosphere called the Great Red Spot. We don't know how long that's been there. Hundreds of years at least, possibly thousands of years. Over shorter periods of decades, it changes shape, so it narrows, and it's getting narrower to the point where it's not quite circular today, but it's getting there. There's a recent picture of the Great Red Spot. I think this is probably taken by the Juno spacecraft, and this is just an immense storm rotating in the atmosphere of Jupiter. The red colors come from compounds like phosphorus, which kind of are dredged up from the lower cloud decks to the surface. The Juno spacecraft is currently in orbit around it, and it gives us great views of the top and the bottom that we can't see from Earth. So you can see these incredible storms near the poles of Jupiter. And again, look around the North Pole here. This is just a series of storms, each one about the size of the Earth, rotating around the North Pole. This is a false color picture, but you get the idea that Jupiter is a really turbulent, ever-changing environment. It has a system of rings as well. They're not easy to see, and they weren't discovered until the Voyager spacecraft flew past in the late 70s. So this is a very tenuous series of rings, nowhere near as impressive as Saturn's rings, but they do exist. Jupiter has a magnetic field. If you could see it with your eyes, it would look that big in the sky. It is just, it's bigger than the sun, the magnetic field of Jupiter, and it extends almost all the way to the orbit of Saturn. Now, the next planet is probably, I don't know, is it everyone's favorite planet? It's certainly the one that draws a gasp when people see it for the first time. It's not as massive as Jupiter. It might look about the same size in pictures, but it's about 1/3 the mass of Jupiter. It's about twice as far from the sun as Jupiter, so the gaps between the planets are getting really big now. It takes nearly 30 years to go around the sun. It rotates very quickly as well, about 10.5 hours. And again, it's got more, it's got hydrogen and helium in it, but Saturn emits more heat than it absorbs, so it takes in sunlight and other radiation from the sun, but it emits more, and we think that's because Saturn is, within it, shrinking. There's a layer of helium which is raining down onto the core, and that's emitting heat, kinetic energy as it strikes the surface of the interior, the core of the planet, and releasing additional heat. These are discoveries which have been made by the Cassini mission, which orbited Saturn beginning about 2004, and returned these incredible images of the rings of Saturn in detail, which is just exquisite, and also the moons of Saturn as well. This is possibly my favorite picture taken by the Cassini spacecraft, and it's an eclipse of the sun viewed from the Cassini spacecraft as Saturn passes in front of it. So sunlight is illuminating the faintest of Saturn's rings, and it just looks weird because it looks like the rings possibly go through the planets, but it's just a confusing mixture of light and shadow. Light from the rings which are reflecting onto the night side of Saturn, and also the shadows of the rings as well. They're kind of on the planet. And that blue ring was a newly discovered feature by Cassini. We can't see that from Earth. It had to take the Cassini spacecraft to travel around to the night side of Saturn to view it. The rings of Saturn are not a solid object. We've known that they can't be for at least a couple of hundred years. And this is an artist's impression. The Cassini spacecraft never got this close to the rings, but we know that the rings are built up from ice, which basically coalesces together to make slightly bigger particles. But they can't get too big because then Saturn's gravity would disrupt them into smaller pieces again. But the rings of Saturn are made of billions and billions of small icy particles. All of them, you can think of them as being little moons in orbit around Saturn. And when viewed from a great distance, they look like this solid set of rings. This is a Cassini spacecraft image taken near the solstice, or the equinox, sorry, on Saturn, where the sun was basically shining along the edge of the rings, and it was casting these really long shadows from, you know, features which are probably only a few meters high along the edge of the ring, but they've got such long shadows during this part of the season. Now, the rings of Saturn are not a permanent fixture, so we're kind of lucky to be living in the age where we can see the rings of Saturn. They're likely only to have existed for 100 million years. So there was a debate about whether maybe Saturn broke one of its moons apart and that material formed a ring, and the ring formed billions of years ago, or whether it was formed from a small moon which was destroyed fairly recently in the history of the solar system. Well, the Cassini mission has provided the answer. We now know that the rings are very young and that they won't last for too much longer. In its final dive into Saturn, Cassini flew between the planet and the rings, and it sampled a rain of material from the rings. The rings are actually very gradually raining down into the planet, so they're going to disappear within a few 100 million years. So if, you know, the age of the solar system is 5 billion years, give or take, these rings have existed for just basically a tiny fraction of that time, and they won't be here in a few 100 million years' time. So mostly Saturn is a planet without rings, and we're just lucky enough to live in the time where we get to see them. Further out, we've got planet Uranus. Again, it's a system of rings, and the angle of that picture wasn't just so that I could fit the picture on the slide. It genuinely does look like that. Uranus is a planet which is tipped on its side. Its angle is 98 degrees. So the Earth is 23 degrees. Most of the other planets aren't much different to that. This is a planet which is tipped over on its side. It's a much less massive planet than Jupiter and Saturn, so just, 15 times the mass of the Earth. It's nearly twice as far out, or it's more than twice as far out as Saturn is. And we think that Uranus was put into that condition by, again, another giant impact a long time ago, which tipped the planet over. It's interesting because this planet has seasons, and the seasons last for about 42 years. So one pole is pointed towards the sun for 42 years, and then as it's around the other side of the sun, the other pole gets 42 years of daylight. So it's very, very unusual, and that does actually impact the climate on the planet and the weather. When the Voyager 2 spacecraft flew past Uranus in 1986, it was very quiet. There was very little to see, very little weather. And it was only when the Hubble Space Telescope and its cameras were fixed in the 90s and 2000s that we began to get pictures like this one, which showed that actually Uranus is quite an active planet, and it does have weather systems and bright clouds and so on. Neptune looks a bit like this. All the pictures of Neptune show this really deep blue, but actually it's because the Voyager cameras weren't calibrated correctly. It's actually the same color as the planet Uranus. The reason it looks that color is because the filters that they used on Voyager 2 weren't red, green, blue. There was something like red, violet, and orange. And when they combined them, they weren't able to kind of make a true representation of the planet at that time. So there are corrected versions of this around, and especially the new images taken from Hubble show the true color more accurately. So it is basically the same color as the planet Uranus as well. It's very similar. It's a little bit more massive, but it's about the same size. And again, it's like 30 times the Earth's distance from the sun. It takes 165 years to go around, and that's it. That's the end of the planets. Now, there are other objects in the solar system beyond the planets, and I want to kind of like talk about those as well. Now, the first population we should mention fits into that gap between Mars and Jupiter, and it's the asteroid belt. The first one, Ceres, was discovered at the start of the 19th century. Astronomers were deliberately looking for small planets between Mars and Jupiter. When they found Ceres, they were kind of like not really surprised by the fact, but also a little disappointed by the fact that it wasn't a major planet. Others were discovered in the years that followed. So Vesta was the second. It was discovered in 1807. And since then, we now have a total of more than 1 million asteroids in the asteroid belt. And that number is going up by tens of thousands, if not hundreds of thousands every year. 20,000 of them come within the Earth's orbit. So we're kind of in the middle of a swarm of about 20,000 asteroids. They're not all confined to that asteroid belt. Jupiter stirs up the asteroid belt and throws some of them towards the inner solar system. And of that total, about 2,000 will likely hit the Earth at some point in the future. So they're classed as potentially hazardous. I just want to focus on the two biggest asteroids because we've got good pictures of them. The Dawn mission returned this picture of Ceres, the biggest one. It has a diameter of about 600 miles, and it's kind of in the middle of the belt, and it takes nearly 5 years to go around the sun. It has a differentiated structure, which means it has a crust, it has a mantle, and it has a core. And those white spots on the surface are salty deposits because water wells up from the surface, from beneath the surface of Ceres, and then it evaporates, but it leaves all the salt deposits behind. So we think that Ceres has a large kind of internal body of water within it, and Ceres is thought to be kind of one of the building blocks of the solar system. It's objects like Ceres and Vesta, which build and come together in the early days of the solar system to form bigger planets. So these are sometimes referred to as planetismals when you see discussions of the early days of the solar system, but they're talking about things like asteroids. So Vesta's a little bit smaller, and it takes nearly 4 years to go around the sun. And again, there are lots and lots of objects like this, and the asteroid belt might have a profound effect on our future kind of evolution as a species, because there are a lot of resources in the asteroid belt, a lot of minerals, precious metals. They're possibly a gateway to exploring the wider solar system because of the existence of things like water on their surfaces. I think maybe me and Paul are going to do a talk about this at some point, but we will see. Just to give you a size comparison with the moon, the total mass of the asteroids in the asteroid belt, although they look quite big there, they total about 3% of the moon's mass. Comets are other small objects in the solar system. So, you know, hopefully everybody got to see Comet Neowise and the brief opportunities that we had a couple of months ago. But comets appear in our sky. They're derived from long-haired stars, or the word for a long-haired star. And a few of them are periodic, like Halley's Comet, and some of them seem to drop in and are never to be seen again. They show tails which grow as they approach the sun. They sometimes show a distinctive green colour, or sometimes a golden tail, or sometimes a blue tail. They swing in on very elliptical orbits and then head back out again, and some of them return because their orbits aren't that big, and maybe they go out as far as Jupiter or Neptune, but they come around again regularly. We live in an age where we've sent spacecraft to the surface of these things. So this is a picture from the surface of a comet called 67P by the Rosetta spacecraft. And again, you're looking at a terrain which looks mountainous. The overexposed parts are in sunlight. The night side of the comet, well, it's kind of filled with a hazy kind of glow, and that's because there is material erupting from the surface, which eventually goes into forming the long tail. Comets are tiny, just, like a mile across would be a decent sized comet. So it's not a very big thing, but its atmosphere, the stuff that begins to evaporate and form the coma of the comet, can be huge. It can be bigger than the sun sometimes. The green glow comes from the glow of a certain type of carbon fluorescing in ultraviolet light. The solar wind, this constant stream of particles, pushes the tail away from the sun. And the tail can be incredibly intricate. You can have a dust tail, which is made from the dusty particles on the surface of the comet, and an ion tail, which is straight, which is caused by, again, sunlight ionizing carbon monoxide. So a dust tail and a gas tail from the comet, and it's sunlight which drives this. But these are small objects. Now, comets release a lot of material along their orbit, and if the Earth happens to pass through the trail of a comet, then these particles of dust can burn up in the Earth's atmosphere, and we see a shooting star or a meteor. And at certain times of the year, we get meteor showers where you see a whole lot more meteors than you do on other nights. The most recent was the Perseids, which was just clouded out here, as usual. And the next meteor shower will be the Orionids in October. So there are some good nights to go out and look, but meteors are linked to comets. So here's the picture of a comet trail and the Earth's orbit, and sometimes the Earth can go through both points of intersection, or maybe the angle of the comet's orbit just allows us to go through one. There are some comets we just never meet. They don't cross our orbit. Interestingly enough, Mars has its own set of meteor showers. Mercury has its own set of meteor showers. So Mercury passes through the orbit of Comet Encke, which goes around the Sun every 3 years. So Mercury experiences a lot of meteoroid strikes as well because of that. And because Mercury is closer to the Sun's gravity tends to be making things travel a lot faster. So Mercury's surface has been pummeled by meteors for billions of years, and that's why it kind of looks as dark as it does, even darker than the moon. Now there's dust everywhere in the solar system, so we've got things like comets which release dust, but also asteroids have them as well, and asteroids can bump into each other and collide. And this just means that there's dust throughout the plane of the solar system. So throughout the orbits of the planets, there is dust, and you can see this dust very easily from the equator after sunset. It's a bit harder to see from Northumberland, but it is possible if you look at the evening sky during spring or the autumn sky before sunrise, and you can see a kind of cone of light before twilight arrives, and this is the zodiacal light, and this is sunlight scattering off all the dust in the solar system between the planets. And it also includes the asteroid belt as well, so you're kind of in a way looking at the asteroid belt. I guess the most famous trivia bit about this I could tell you is that this is the subject that Brian May studied before he went off to join Queen, and the subject he rejoined much later to complete his PhD studies with. Pluto, no longer a planet, okay, and quite rightly so. You might agree with that, you might not agree with that, but Pluto belongs to a population of other objects. So if Pluto is a planet, these other things as well should be planets. And quite often the argument you hear against Pluto not being a planet is that school children learned it in school. We want it back for like cultural reasons like that, but astronomers are heartless people. They have hearts of stone in general. And they had a very dispassionate discussion about this in 2006 and decided that planets are things that are round. They go around the sun and they've cleared their orbit of other material, and Pluto just hasn't done that. Not every astronomer agrees with this definition, even now, even 14 years after the decision was made, there are astronomers who don't agree with it. But it is definitely a different kind of object to all the things we've seen so far. It was discovered in 1930. It is tiny. This thing is smaller than the moon, and it orbits in a way which takes it sometimes, for a period of about 20 years, closer to the sun than Neptune, and then back out again much further. It does have a thin atmosphere. I'll be able to show you that in a moment. There it is, the atmosphere of Pluto. So it's the largest of the Kuiper belt objects. It has an atmosphere of methane and nitrogen. It is active on its surface. It has a big moon called Charon. Its surface is geologically active. It's incredible that something out where the temperature is minus 240 degrees Celsius still seems to be active. That heart-shaped region, for which Pluto is quite famous now, is actually the active region. It's smooth and flat because it's warm. There is something beneath the surface of Pluto keeping the temperature high enough for liquid to exist and for it to occasionally, oops, I've lost that. Hang on a second. I think I've lost my screen share. Just give me a second. Can somebody give me a thumbs up if you can still see the Pluto slide full screen?
Yeah.
Right, okay, thanks. So yeah, Pluto's still active. I mean, it just shows you that all the way out to the edge of the solar system, there are still processes going on. Nothing's dead out there. Now, Pluto is part of the Kuiper belt, and the Kuiper belt actually is related to the comets that I was telling you about. Now, I went through a lot of this when I talked about comets a little while ago in a previous talk, so I don't want to labour the point here. But there are two groups of comets that astronomers have discovered in the last few hundred years. One of them are short period, like Halley's, which goes around every 76 to 77 years, and so it's constantly coming back. And there seem to be other comets which have periods of thousands or even tens or hundreds of thousands of years, and which just go way beyond the orbits of all the planets. So you've got a short period and a long period. And these tell us about the outer solar system. Now, the Kuiper belt was postulated to be the source of the short period comets like Halley's Comet. The idea is that these comets go around the sun, and eventually the sun basically boils them away to the point where they're not comets anymore. They're just inert objects going around the sun. So that would happen quite quickly. So 1 million years from now, we're not going to see Halley's Comet anymore, but we'll see another comet which will have taken its place. So these objects are being replenished, and the idea is that it's being replenished by a zone beyond Neptune. So this was, people speculated about this long before it was discovered. So it was something like the 1930s to the 1950s, and then the first object was discovered in 1992. Actually, the first one was Pluto, but people thought it was a planet at that point. For this other class of comet, the one that drops in from any part of the sky on these very long orbits, we think there's something called the Oort cloud out there. And again, this is so far from the sun that it's never been directly observed, but it has to exist to be the source of all of the other comets. Comets like Neowise come from the Oort cloud. So it surrounds the solar system, and comets are maybe perturbed by passing stars, which change their speed very slightly and cause them to fall in or to fall out of the solar system. But the ones that fall in are the ones that become the dramatic comets that we see. So there's a lot of indirect evidence for the Oort cloud. We've seen many objects in the Kuiper Belt at this point, and the most recent was Arakoth. This is the spacecraft which flew past Pluto, then went on to fly past Arakoth a couple of years ago. And again, these are the true building blocks of the solar system, and we've actually got like something frozen in time almost. These are two objects which have very gently coalesced to make a bigger object, but then because there's so little out there, it's just been preserved in this state for billions of years. So it hasn't participated in the planet building that maybe other objects like that have. At the moment, we know of nearly 2,000 of these objects in the Kuiper Belt, and Pluto is the biggest one so far. There's a map as of 2015. It's a bit out of date, but you get the idea. Pluto is in amongst that mass beyond the letter N. So Pluto is just one of those. So if Pluto is a planet, why aren't the rest of them? And if the rest of them aren't planets, then neither's Pluto. Okay, so that's how things stand at the moment. Some of the other objects out there are comparable to Pluto. So these are artist's impressions, but we've got Eris, Marke, Haumea, and some of these have their own moons. So there's a Hubble Space Telescope picture of Eris with its moon Dysnomia. Beyond those, we have various objects which have been scattered by Neptune. So gravity from Neptune, if they approach Neptune too quickly, it can cause them to be scattered into much bigger orbits. And there are really strange objects out there which take hundreds and thousands of years to go around the sun. And we're really only at the beginning of being able to explore this part of the solar system. The Oort cloud is out there too, probably 50,000 times further out than the Earth is. And all of the spacecraft that we've sent out are nowhere near being at the inner boundary of this yet. It's going to take hundreds of years for our spacecraft to begin to touch the inner boundary of this thing. So by that point, their batteries will be dead. We won't be able to pick them up. So we're not going to be able to explore this region for a long time yet. Now, where did all this come from? Okay, so I want to talk briefly about the origin of the solar system. So the big picture is the solar system formed when a dense cloud of gas and dust collapsed nearly 5 billion years ago. The picture you're looking at there is of part of the Orion Nebula, and what it shows is a kind of gassy, dusty background. So that's the Orion Nebula, and within it, part of the nebula has collapsed and coalesced to form a protoplanetary disk. So this yellowish blob here is much bigger than the current solar system, but it's on the way to forming a star in the middle and a dusty disk of material around it, which will one day form planets. So the original cloud from which our solar system formed was probably like the nebulas we see in the night sky. They're like 50 light years across. For comparison, the nearest star to us is 4 light years away. So these things are absolutely immense. And when they collapse, they don't collapse like collective, in a singular way down to a single cloud. They collapse and fragment, and these fragments collapse, and then they might fragment, and then you keep getting all of these different pockets of fragmentation. And eventually they're small enough to begin to collapse into a single place where a star will form, and you get these protoplanetary disks. So when the sun formed from its nebula, we think it formed an open cluster with about 1,000 to 10,000 other stars. So where did they go? Well, it's more like the sun left. So these stars, when you see them, star clusters, they're not particularly close to each other, but they do pull on each other. And the ones near the outer edges are not held very tightly, and they're able to escape. And the sun probably escaped after a few 100 million years. So that sounds like a long time to hang around, but it's still not that much compared to 4.6 billion years. So the sun escaped the cluster fairly early on. We know this to be true because in the meteorites we've discovered on the Earth, we have evidence of elements that could only be formed in supernovas trapped within the material of the meteorites. So that tells us that supernovas exploded before our solar system, and it's likely that the shock wave from the supernova spreading outwards compressed part of the nebula and caused it to begin to collapse. So we are here because a star died, at least one star. It took about 50 million years for that collapse to form the sun. 50 million years. Again, these numbers are huge, but it's really quite a quick process in terms of the age of the universe. So the material collapsed and formed a disk. Within the disk, any small kind of like particles were attracted to slightly bigger particles, and those particles grew by pulling in more material, and you get the planets forming within the disk of material. And that's kind of the big picture of like how astronomers thought solar systems formed, especially ours. But the thing is, with only one solar system, you invent something to explain it. How do you know it's right? Because you've got nothing to test it on. You've invented something which explains what you can see, but how do you know it's right? How do you know there isn't another explanation? And that's the problem that astronomers had until they started discovering planets around other stars, and were able to test it by comparing our solar system to other solar systems. So there are various things which this simple kind of model of the solar system fails to explain. So for example, I haven't really gone into it, but there was an episode about 500 to 600 million years after the solar system formed, where a lot of new craters were formed on the planet. So things were very kind of chaotic and busy at the start, where the planets were forming, being hit by asteroids and building themselves up. And then everything went quiet and the planets were happily going around the sun, but then it kicked off again after 500 million years, and you have chaos raining down on the planets. Why did that happen? Why is Mars so small? Why is Mercury such a small planet with a huge iron core? There are kind of like things we've learned about the solar system in the past 50 years, which this theory just can't account for. It doesn't kind of like explain why we have this number of planets. Why don't we have like bigger versions of the Earth, like really big rocky versions of the Earth? So there are various shortfalls in our standard theory of why the solar system formed. Why is the asteroid belt like that? When we do models of the solar system, and like the original nebula, when it collapses and forms an asteroid belt, it's packed with a lot more asteroids than we currently see. Why is there no big planet there? And again, there are other shortfalls in our kind of like theory of growing planets from small pieces, but we couldn't really figure out what the missing piece was. What do other solar systems look like? Well, in the years since the 1990s, we've discovered 4,200 planets around other stars, and they're within 3,000 different solar systems. So we've got a huge sample of solar systems to look at now. So if we want to kind of like test our theories of how you form planets around a star, we've got more than just the one that we had 50 years ago. So we can look at our models and run them against other stars and see if they compare well or favorably or whatever. It turns out that other solar systems have a huge diversity of planets. I've talked about gas giants and ice giants. What we've discovered around other stars are hot Jupiters. So these are things which are like Jupiter, in some cases much bigger. So they're bigger versions of Jupiter, but they orbit closer to their star than Mercury does to our sun. So they're basically boiling away very, very close to their star. There are rocky planets like the Earth, but much more massive, like 10 times the mass of the Earth, but with a solid surface. So they've been called super Earths. In our solar system, there's nothing really between the size of the Earth and the size of like Uranus and Neptune. In other solar systems, we've discovered these kind of giant worlds, and they're called mini Neptunes. they're a really imaginative bunch of people, these astronomers who name these things. Anyway, mini Neptunes. So we see these planets are kind of commonplace in other solar systems, but not ours. Why don't we have any super Earths? According to our models, we should have several of them in the inner solar system. We only have one Earth, and it's not a super Earth. Well, it's super for us, obviously, because we live on it, but it's not the same scale. What's gone on? It turns out that planets can migrate. They can move over time through their solar systems by interacting with other planets or with the disk of material that was there at the start. So the big discovery, that the thing that we learned from other solar systems was migration. Now, how migration works is, if you imagine your solar system forming, you've got your star in the middle and your planets going around it. Initially, there might be a lot of gas left over from the formation, and the gas pulls on the planet because it has mass. So the gas pulls on the planet pulls on the gas, and that means the gas speeds up or slows down the planet. And if you speed up or slow down a planet, it means that it goes into either a bigger orbit or a shorter orbit, a smaller orbit around the star. But the point is, it migrates. It doesn't stay in a fixed position. If you've got icy objects or rocky objects like planetoids and asteroids and Kuiper belt objects, if these happen to pass close to a planet, they might pull on it a little bit, but if millions of them do it over periods of millions of years, it all adds up. It all works to change the orbits of a planet. So this is the missing ingredient. We assumed that when our solar system formed 4.5 billion years ago, that was it. It formed, and then it's basically been working like clockwork since, and that's not the case. It's actually been quite a dynamic place, which has been changing over time. So the two mechanisms are migration, where the planet interacts with a disk of gas, which might have been there at the start, and scattering, which is still going on now. This is where planets can encounter small asteroids, and the asteroid's path gets changed, but also the orbit of the planet gets changed a little bit, and these are the effects that add up. So the planet's orbits are changing, and if the planet's orbits change, maybe then the planet gets too close to another planet and begins to pull on it and change its orbit. So that's what we think the history of the solar system is most influenced by since the formation. So this is kind of the timeline that's been worked out in the last 5 to 10 years. So we think Jupiter was the first planet to form because it's the most massive one. It's had the most time to grow, and it formed much closer to the sun than it is at present. When Jupiter formed, there was still a lot of gas within the solar nebula, and the gas influenced Jupiter in such a way that it migrated inwards. So it started spiraling inwards towards the sun until it reached the approximate position of where Mars is. So there's actually a lot of rocky material in this part of the solar system, and Jupiter scattered it. So a lot of the asteroid belt that was originally there was basically kicked out of the solar system or collided with Jupiter. So it reduced the amount of material that was available for the planets in the inner solar system. So no super Earths here, because Jupiter happened to spiral inwards during the early days of the solar system. It's also possible that Mercury formed further out and was scattered inwards by Jupiter as well. So Mercury might have formed further away in the asteroid belt. There are certain signatures on its surface which indicate that that might have happened. Saturn formed a little later, and it too migrated inwards, and it caught up with Jupiter, and Saturn's gravity and Jupiter's gravity halted Jupiter's inward rush and reversed it, so that Jupiter and Saturn ended up spiraling outwards back towards where they are today. This has kind of been verified by supercomputers running the equations with lots of like random variations, and this is what happens a lot of the time. Jupiter and Saturn migrate until you have them back to where they are. In the outer solar system, Uranus and Neptune form, but probably not in that order. Neptune probably formed closer, but Beyond the orbits of these two, you've got these icy objects which will become comets eventually, the Kuiper belt, and whichever the outer planet was interacted with the Kuiper belt, and that meant that the orbit of the outer planet changed and began to migrate, and this influenced the orbits of the other planets. And eventually, after 500 million years of this, Jupiter and Saturn were orbiting in such a way that they were kind of flinging objects left, right, and center across the solar system. They were stirring up all of these icy objects, and it created this new bombardment 1 billion years after the birth of the solar system. And eventually, after that scattering event had happened, the solar system settled down to how we see it today. So that's the kind of tumultuous history that we have. Now, the Kuiper belt scattered by the outer planets into these very, very long period orbits which form the Oort cloud. So the Oort cloud has been built up over time by these comets being thrown out of the inner solar system by the planets, and they form this kind of spherical structure because as things get further away from the sun, they move more slowly. So by the time it gets out to like 50,000 times the Earth's distance, it's moving just like a few meters per second, very, like walking speed almost. And because it's out there for millions and millions of years, the Earth, the sun, and the solar system are moving through the galaxy. And if it's out there for millions of years, it'll get disturbed by stars, which pull on these objects as well and circularize them around the sun in random directions. So these things which might have started out in elliptical orbits, because they're spending so long out there, their orbits get changed by passing stars, and they become built up in this shell of material around the sun. So that's where we think the Oort cloud came from. It was formed from the Kuiper belt. Right, that's the end of the theory part of it. I'm aware that I've talked for just over an hour. So what I want to do is to, just before I do this very brief last bit, is to ask if anybody has any questions. If anybody wants to ask anything at this point, or type it into the chat. It gives me a chance to have a quick sip of coffee. Okay. Right, so look. Our view of the night sky is influenced by our position in the solar system. Now, the word planet comes from wandering star, and to illustrate that, I've plotted the position of Mars as it moves through the constellation Taurus next year. So you've got the Pleiades star cluster, and this is the motion of Mars every 2 days. So is that 10 days? It's, 2, 4, 6, 8 days. 8 days. So planets are basically stars which move through the constellations, and that was our working definition of a planet until 2006. So each planet moves in a slightly different way, and it depends on where it is in relation to the Earth. So I want to kind of show you the motions of the planets. Astronomers classify Mercury and Venus as inferior. That just means they're inside the Earth's orbit, and because of that, they're always going to be in the same direction as the sun when you view them from Earth. So in the picture, you've got the Earth, and you're looking towards Venus, and Venus might be behind the sun. We call that superior conjunction, or it might be between us and the sun, which is inferior conjunction. In either case, you can't see Venus or Mercury when it's in conjunction with the sun. The best time to look for these planets is when they're near their furthest angle from the sun, and that occurs at an eastern or western elongation. So basically, in this picture, I'm going to reach for my pen here. Here we go. Let's see if I can do this. So when you're looking from the Earth, you're kind of looking at, let's see, this angle here. You want that angle to be big. I mean, if it was here, the planet, that angle's very small, so it's very close to the sun when it's there. Where I've plotted the planets there, that's about as good as the planet can be in the sky. That's as far as it can be from the sun, which means after sunset, the planet is still quite high, but because the Earth's turning, it'll follow the sun down For Mercury, you've got a very limited window of opportunity to see it. You've got maybe an hour at best after twilight, and for Venus it's up to about 4 hours, so it's a bit better. It's actually easier to observe these planets during the day when they're higher in the sky if you want to see more detail on them. So you get superior conjunction. Remember, the Earth and the planet are going around the sun, so this thing's constantly moving, but you see the same cycle of events over and over. So you get superior conjunction where it's not visible, then it'll be in the morning sky for a bit, then it'll be at maximum elongation, and then inferior conjunction. And then it'll be eastern elongation in the evening sky, and then maximum eastern elongation, and then superior conjunction. So it follows this kind of process, and your view of the planet, Mercury or Venus, will change very dramatically depending on how it's illuminated by the sun. So if you're looking in the evening sky, when it's near superior conjunction, it looks almost fully illuminated, but the downside is it's very far away from you because it's on the other side of the sun. So it looks very small and difficult to see through a telescope. As it gets closer, it gets bigger, but the downside is it's less illuminated, so there's less of it for you to look at. And this is true for Mercury or Venus, and it's repeated in the morning sky as well. I guess the ideal time to look is just after greatest elongation, but you haven't got very long. It tends to be moving very quickly as it approaches the sun. For the outer planets, for superior planets, that's Mars out to Neptune, the view is much more convenient because it's outside the Earth's orbit. The planet can be on the opposite side of the sky to the sun. So in this picture, when the planet's at opposition, that means it's nearest to the Earth, and also it's visible all night. It basically rises at sunset, it's highest in the sky at midnight, and it sets at sunrise. So that's the ideal time to look at a planet like that. And for Mars, that's coming in October. So that's a good thing. I'll tell you about that in a moment. When it's in conjunction with the sun, you can't see it, so it can be very, very far away from you and invisible. These things of quadrature just means it's kind of making a right angle, a 90-degree angle with the Earth and the sun. So any time between quadrature and opposition is a good time to view the planet. I'm going to skip some of these because I think we probably don't need to go into this. But basically, the synodic period is what we're interested in for a planet. You've got what you call the sidereal period, which is the length of its year. So the Earth's sidereal period is 365 days. For Mercury, it's 88 days. What we're interested in is how often can you see it in the evening sky or the morning sky. And it's like waiting for the hands on a clock to line up. If they're lined up at 12 o'clock, they're lined up next, just after 1:05. For the planets, you can work out that time, and it's called the synodic period. So a planet like Mars will be well seen in the evening sky every 780 days on average. The Earth, Mars, and the Sun line up every 2 years for Mars. For Venus, it's every 584 days. For the outer planets, well, Jupiter, 399 days. That's basically 30 days longer than a year. So it's like Jupiter comes to opposition 1 month later every year. For Saturn, it's like 2 weeks later every year. For Uranus, it's 5 days later. For Neptune, it's nearly 3 days. It's like they're not moving very much in their orbits in the time that it takes the Earth to complete a single lap of the Sun. I'll show you Mars's orbit because this is kind of something we'll be looking at, I guess, over the next couple of months, because Mars is coming to opposition in October. So the Sun, Earth and Mars will line up nearly exactly on October the 13th, and it's not going to be as good as the one in 2018, but it's higher in the sky, which makes it a lot easier to see from the UK. The distance will be 63 million kilometers, so that's 5 million kilometers more than last time, but again, that's offset by the fact it's much easier to see from the UK. In 2 years' time, they'll line up again, and they'll be much further apart. This is because Mars's orbit is not circular at all. It's very eccentric, very elliptical. So by the time you get to 2029, if we get to 2029, That'll be a pretty rubbish opposition of Mars. But things will improve after that until you get to 2035 again, when Mars and the Earth will be close together in the night, in terms of distance again. So good oppositions of Mars occur every 15 to 17 years. And just one more thing to mention, the rings of Saturn are a nice thing to look at, but because of the tilt of Saturn to its orbit, it means that as Saturn goes around the Sun, although the tilt doesn't change, the angle we view Saturn at does, and it means that the rings gradually close up so that you eventually view them edgeways on. Last year, they were at their most open, so you had a brilliant view of Saturn last year. The rings are a little bit more closed up at the moment. Next year, they'll be even more closed up, and in a couple of years' time, they'll be edgeways on. And so it takes like 7 years to go from fully open to fully closed, and then another 7 years to see them reappear again. This confused Galileo when he first saw Saturn, because his telescope wasn't good enough to resolve the rings. He actually saw a bright blob, which was Saturn, and two little blobs next to it, which he thought were moons. But then they disappeared a few years later, and he thought his telescope was playing tricks on him. And then they reappeared a few years after that, and he could never figure out what they were. But it's the rings. The rings make Saturn look different every year, every time you look at it. Right, I think that's all I want to talk about. So that's a very full introduction to the solar system and how it looks to us. So I'm going to stop there.